right. In this second and last lecture from section 3.2, we're going to take a look at how we can use elementary row and column operations to give us a method of finding the inverse of an invertible matrix. Okay, so we're going to talk about finding inverses of matrices. So to get started here, suppose I've got a matrix, m rows and n columns as usual, and then another one with the same number of rows, possibly different number of columns. So by the augmented matrix, this is what I'm defining. I mean, you basically just stack the matrices A and B next to each other, right? So that matrix, you can read it any way you like, the augmented matrix AB. It has the same number of rows that A and B do, but its number of columns is n plus p. You sum the number of columns. The first n columns come from A, the last p columns come from B. So you just stack the two matrices next to each other and you get an M by N plus P matrix. It's called the augmented matrix, A by B. Okay, there's an exercise, it's exercise number 15 in this section, that if M has the appropriate size, it has the right number of columns. When you multiply M by an augmented matrix, you get an augmented matrix that you get by multiplying each kind of component by M. Okay, so that's just a matrix multiplication exercise. I'm going to leave it to you. So I'm interested in the case when we're talking about invertible matrices. So if A is invertible, so it has an inverse, if I augmented A, say it's an invertible matrix that's square with n rows and n columns, if I augment A with the identity matrix and then I multiply that by A inverse using that exercise, well, A times A inverse is certainly the identity matrix, and A inverse times the identity matrix is A inverse, so I would get that augmented matrix. All right. One of the many corollaries of theorem 3.6 last time said that every invertible matrix A is a product of elementary matrices. Elementary matrices corresponding to either elementary or row or column operations. So if we think about what that means, if we take this augmented matrix AIN and we multiply it by that product of elementary matrices, we get the matrix augmented INA inverse. So if you just translate that into a sentence, it says that you can transform the augmented matrix AIN into the matrix INA inverse with a finite number of row operations. Okay, you can use it because left multiplying by an elementary matrix corresponds to an elementary row operation because the products are on the left. Cool. Flipping that around, suppose that I took some matrix M, it's a product of K elementary matrices, and I left multiply this augmented matrix by it, I get IN times, or IN augmented with B. Suppose that I get that, okay? So what would that mean? That would mean that M times A augmented with M, because that's what the left-hand side would be this IN augmented with B. So there's sort of two equations I can get from that. First of all, that MA has to be IN, the kind of component on the left of the augmented matrices have to be equal, and also on the right. So on the right, it would mean that M has to be the matrix B. Well, this first equation, MA is equal to IN, it means that M is a left and hence two-sided inverse. So first of all, the matrix A is invertible and M is A inverse, but M is equal to B. So the two conclusions I'm getting from that is that A is invertible, A inverse exists, and B is its inverse. Okay, so if you roll all that together, or I guess, sorry, if A isn't invertible, I have one more thing to say before we roll it all together. If A isn't invertible, then multiplying this augmented matrix by an invertible matrix M could never give you such a thing. So why is that true? If M times that augmented matrix were IN augmented with B, well, then you could transform A into the identity matrix with a finite number of row operations. Remember, because every invertible matrix is a product of elementary matrices. So if we could transform A into IN with a finite number of row operations, then by theorem 3.6, the rank of the matrix A would have to be N, because performing row operations doesn't change the rank. But if the rank of A were N, then A would be invertible, but we're assuming that A isn't invertible. Good. So if you roll all that together, stop the video and rewatch it if you need to. What we've proved is the following theorem. The author doesn't state it as a theorem in the book, so I won't number it. But the theorem says if you take a square matrix, that it's going to be invertible. It's going to have an inverse if and only if there's an invertible matrix M, or if you prefer a product of elementary matrices. You can write it like that, so that when you left multiply the augmented matrix A with IN, you get the augmented matrix IN with B, and B will be its inverse in that case. All right, so a matrix is invertible if and only if you can sort of transform it with a finite number of elementary row operations into the n by n identity matrix. And if you do that transformation to the augmented matrix, A with IN, when you're done transforming A into the identity matrix, the other side, quote unquote, will be the inverse of A. Nice. Let's end this short video with just an example here. So I've got a 2x2 example. I take the matrix A to be, and actually before we look at this example, I should say that this theorem is saying that it's invertible if and only if. So if you start trying to perform these elementary row operations to the matrix A, and you cannot get the identity matrix in the left-hand side, then the matrix is not invertible. So this is kind of an algorithmic way of simultaneously determining if a matrix is invertible and what its inverse is. So maybe I'm interested in this matrix, and I'm wondering, is it invertible? If so, what's its inverse? I can answer those questions simultaneously by taking the augmented matrix. Let's just look at the computation together. So I just augment the matrix A with the 2x2 identity matrix. You don't have to draw this augmentation line, but I think it's kind of handy. And then I'm doing some row operations. Yeah, what did I do in this first row operation? Let me write them off to the side here. I just interchanged row 1 and row 2. I interchanged row 1 and row 2. And then it looks like I replaced row 2 with row 2 minus 2 times row 1. So I did a type 3 elementary row operation. Again, you can keep drawing the augmentation thing if you want, but it's not necessary, but I am keeping track of this is two 2x2 matrices next to each other. Okay, then what? I think the next row operation I'm going to do is I'm going to replace row 2 with minus 1/3 of row 2, right? Giving myself that so-called leading 1. Okay, and then what? I'm going to replace row 1. I'm replacing row 1 with row 1 minus row 2. I'll leave it to you to check the math, but that ends up giving me that thing. And now we've succeeded. So the left-hand side is now the n by n identity matrix, or 2x2 identity matrix. So our theorem says that, first of all, A is invertible because we ended up getting the identity matrix on the left-hand side. And what's A's inverse? It's the transformed matrix on the right-hand side. Okay, that was a short one.